Hello and welcome. In the previous lesson, we learned about the external interrupts, implemented the ISR for the same, and did some programming exercise. In this lesson, we shall learn about the pin change interrupt and implement an ISR to handle such interrupts. The Atmega 328 microcontroller supports 23 pin change interrupts. However, all the interrupts can't be used as the pins share the functionality. For example, the pin number 1 is the pin change interrupt 14, but this function of the pin 1 is shared with the external reset. So, if you are using pin 1 for external reset, then it can't be used for pin change interrupt. The microcontroller provides so many pin change interrupts and external interrupts are also available. But what is the difference between the external interrupts and pin change interrupts? Despite the microcontroller provides 23 pin change interrupts, there are only 3 interrupt vector for these interrupts. The interrupt vector at addresses 06, 08 and 0A in hex are for pin change interrupts 0, 1 and 2 respectively. The change in logic level on the pins PCINT23 through PCINT16 trigger the ISR associated with the pin change interrupt 2. Change in logic level on the pins PCINT14 through PCINT8 trigger the ISR for pin change interrupt 1. And change in logic level on the pins PCINT7 through PCINT0 trigger the ISR for pin change interrupt 0. It is programmer's responsibility to identify the occurrence of interrupt on the particular pin and take appropriate action. The register PCICR, that is pin change interrupt control register, PCIFR, that is pin change interrupt flag register, PCMSK2, that is pin change mask register 2, PCMSK1, that is pin change mask register 1, and PCMSK0, that is pin change mask register 0, are associated with the pin change interrupts. Let's look into the details and function of each registers. The pin change interrupt control register is used to enable or disable the pin change interrupts. The I flag in the status register must be set for PCICR to take effect. The bit 0, that is PCIe 0, is used to enable or disable the pin change interrupt group 0. Similarly, bit 1, that is PCIe 1, and bit 2, that is PCIe 2, control the pin change interrupt groups 1 and 2 respectively. Logic 1 enables the corresponding interrupt group and logic 0 disables it. The offset of the register is 68 in hex, and the instructions load store is used to read and write to the register. The pin change interrupt flag register is used by the microcontroller to remember the occurrence of the interrupt. The bit 0, that is PCIF0, is used to remember when any of the interrupts occur in the pin change interrupt group 0. Similarly, bit 1, that is PCIF1, and bit 2, that is PCIF2, remember the occurrence of interrupts in pin change interrupt group 1 and 2 respectively. The microcontroller clears the corresponding bit in the register PCIFR by writing 1 once the interrupt service routine is executed. The software can also clear the corresponding bit by writing 1. The offset 3B and 1B in hex are used to reference the register in memory mapped and IO mapped modes respectively. The bits in register pin change mask register 2, pin change mask register 1 and pin change mask register 0 are used to enable or disable the corresponding pin of the pin change interrupt. The I flag, that is interrupt enable flag, in the status register and the corresponding bit in the PCICR must be set for the content of PCMSK registers to take effect. If the bit is cleared, the corresponding pin is disabled and logic 1 enables it. The bits PCINT0 through PCINT7 in the register PCMSK0 enables or disables the pins in group 0. Similarly, the bits PCINT8 through PCINT14 controls the pin in group 1 and the bits PCINT16 through PCINT23 controls the pins in the group 2. The offsets 6D, 6C and 6B in hex are used to reference the register PCMSK2, PCMSK1 and PCMSK0 respectively. The instruction load store must be used to read and write to the registers. Let's implement an interrupt service routine for PCINT12 and PCINT13. The pin change interrupts belong to the group 1 and pins 27 and pin 28 belong to PCINT12 and PCINT13 respectively. The main program controls a LED that blinks every 200 milliseconds. The interrupt service routine controls two LEDs, which will be switched on for 300 milliseconds and switched off before the ISR returns. The ISR must identify the occurrence of PCINT12 and PCINT13 and corresponding LED must be switched on. The LED controlled by the main program is connected to pin number 14 through a 220 ohm resistor, and the LEDs controlled by the PCINT12 and PCINT13 are connected to pin number 15 and 16 through a 220 ohm resistor respectively. Choose LEDs of different color for easy identification. The interrupt signal is generated using the button switches on pins PCINT12 and PCINT13. One end of the button switch is connected to ground through a 220 ohm resistor and the other end to the corresponding pins of the microcontroller. The interrupt pins of the microcontroller is configured in the input mode and pulled high. When the button switch is in off state, the pins are in logic high state, and when the button is pressed and released after a delay, a pulse of logic low is generated and interrupt is triggered. I have rigged up my development board as shown and hope yours is ready too. In the function main, let's configure the register PCICR and PCMSK1. The register PCICR is ORed with the value 2 in hex and the result is assigned back. The register PCMSK1 is ORed with the value 30 in hex as the bits 4 and 5 control the PCINT12 and PCINT13 respectively. Note, ORing the registers with corresponding value preserves the value in rest of the bits. Then, the pins used to drive the LEDs are configured in output mode. The pins 14, 15 and 16 are part of general purpose I/O port B. The bits 0, 1 and 2 in register DDRB is set to configure the pins in output mode. Once configured, writing 1 to the bits 0, 1 and 2 in the register port B switches on the LEDs and writing 0 switches off the LEDs. The interrupt pins, that is pin number 27 and 28, must be configured in input mode. These pins belong to the general purpose input-output port C and correspond to the bits 4 and 5. Writing the bits 4 and 5 of the register DDRC with 0 configures the pin in input mode. It is done by ANDing the register DDRC with the bitwise NOT of the value 30 in hex and assigning the result back. The pins are pulled to logic high by writing the bits 4 and 5 of register port C with logic 1. It is done by ORing the register port C with the value 03 in hex and assigning the result back. The bits 4 and 5 of the general purpose input-output port C is put in input mode as status is read to identify which pin change interrupt has occurred. The logic to identify the pin on which logic has changed is implemented in the ISR. Then the while loop implements the logic to control the LED. It is controlled by the bit 0 in the register port B, ORing the port B with value 1 in hex and assigning the result back, writes the logic 1 in the bit 0 and switches on the LED. The delay of 200 milliseconds is introduced by calling the function delay_ms. ANDing the port B with the bitwise NOT of the value 1 in hex and assigning the result back writes logic 0 to bit 0. Writing 0 in the bit 0 switches off the LED, and again the delay of 200 milliseconds is introduced. The loop executes infinitely and causes the LED to blink endlessly. The ISR is implemented in the function __PCINT1_ISR and placed in proc.c source file. Any change in the logic on the pins PCINT8 through PCINT14 triggers the execution of ISR__PCINT1_ISR. It is necessary to correctly identify the change of logic on the particular pin. It is done by keeping the track of last and current change of the PCINT12 and PCINT13 pins. A global variable of type unsigned character pin C_prev stores the last change of the pins. Note, it is defined as volatile variable for the reasons discussed in the previous section. The current change of the pin's status is read from the register pin C. It is the register used to read the logic level present on the general purpose input-output port C. The change of status of the pins is identified by the XOR operation between the current and the last change. The result of XOR operation is 1 if either bits of the operand is different and 0 if both are the same. Note that the XOR operation only identifies the change, but it does not identify the change from logic 0 to 1 or vice versa. The result of XOR operation is stored in the variable changed_pins, and the pin C_prev is updated with the current pin status. The two if blocks implement the logic to switch on and off the corresponding LEDs. The if statement checks which bit in the variable changed_pins is set by ANDing the values 16 and 32, which are implemented as shift operation. The prototype of the ISR__PCINT1_ISR is defined with the attributes signal, used, and externally_visible as done for interrupt 0 in the previous lesson. The corresponding interrupt vector is also updated with the ISR function name in the interrupt vector table. Compile the implementation and test its working. As you can see, the green LED controlled by the main program is blinking. When the button switch connected to pin number 27 is pressed, the white LED controlled by the PCINT12 blinks. And when the button switch connected to pin number 28 is pressed, the red LED controlled by the PCINT13 blinks. Did you notice we did not configure if the interrupt is edge or level triggered? Can you identify what triggers the interrupt? You will answer these questions by implementing the next programming challenge. Observe the LEDs controlled by the ISR by holding the button switch for longer time. The LEDs are on when the button switch is pressed, then switch off and again switch on when the button is released. This indicates The interrupts are triggered whenever there is change in logic level on the pins. How can you avoid this and make the interrupts edge triggered? With this, we come to the end of this lesson. I hope it was interesting one. In the next lesson, we have a programming challenge where you will change the implementation of pin change interrupt service routine and make it edge sensitive and test the implementation. Until then, happy coding.